Case study 5.2 looks at the core ideas involved in chemical equilibria, because that's the central theme, the central subject of Chapter 5 in this course. And two examples emerge. One is ethanol production as a biofuel, but the second one is the Haber-Bosch process that establishes worldwide fixed nitrogen that supplies the fertilization for crops. So we've talked about ethanol, its disadvantages. In particular, it consumes a massive amount of petroleum-based fuel to produce it, and it competes internationally with the generation of crops to sustain human life through the food supply. So we've talked about that, but take a look at the breakout of ethanol essentials in Case Study 5.2 because it points out some very, very interesting figures. But let's turn our attention elsewhere. Let's look at the Haber process. The Haber process is disarmingly simple in that it's converting hydrogen, H2, and nitrogen to ammonia, NH3. But the important thing about this is that ammonia represents a molecular structure that breaks the triple bond in nitrogen. And it's the triple bond in nitrogen that is so strong that it's very, very difficult to break it. But on the other hand, nitrogen, when it's used to fertilize crops, has this extremely important factor that it can be used as a ladder for oxidation and reduction. And it allows plants to move up and down this ladder to extract energy from the system. So fixed nitrogen supplies the energy requirements for sustaining crops worldwide. And interestingly, almost 8% of the total energy production goes into the formation of ammonia. So it turns out to be very important, both in the energy budget and in the production rate of food. So let's take a quick look at how this works. We start with hydrogen and nitrogen in the gas phase. We feed that into a compressor to increase the pressure. That high pressure hydrogen-nitrogen mixture goes into a reaction chamber. But that reaction chamber increases the temperature, and it also provides a catalyst, typically an iron-based catalyst, in that reaction chamber. So out of the reaction chamber comes our desired product, ammonia, in the gas phase, along with a mixture of hydrogen and nitrogen. And as we understand in this chapter, the chemical equilibria that are set up produce both products and reactants simultaneously in the chemical reaction. That's why we write this reaction as a double arrow. Well, the ammonia is condensed out because it condenses out at a much lower temperature than hydrogen and nitrogen. So that ammonia is then taken to a storage tank and stored as a liquid, but the hydrogen and nitrogen is fed back into the compressor. So this is a constantly operating cycle. And it turns out it's the single most important example of the production of chemical compounds globally in these processes that represent chemical equilibria. And we look at a number of other examples of this in the chapter, but these two processes are highlighted in this case study.